Hello everyone, thank you all for joining me today. My name is Nicholas Monroe. I work as an applications scientist here at Microritics, and today we'll be discussing powder and air interactions. When working with bulk powder materials, it's important to realize that air will occupy a significant fraction of the powder bed volume. Thus, powder and air interactions will contribute to the overall behavior of the powder assembly. When powders are in a low stress state, such as when aerated, the particle interactions will be governed by cohesive forces between the particles. Therefore, characterization of a powder's behavior in such a state will allow us to determine how cohesive a powder is. This testing can also be directly correlated with performance in many industrial processes, such as fluidized beds, pneumatic conveyance, dry powder inhalers, among other applications. All powders will exhibit some degree of attractive forces between particles due to effects like van der Waals interactions, liquid bridging, chemical bonding, or electrostatic attraction. When these interparticle forces are larger than the force of gravity for a given particle, the powder will exhibit a more cohesive behavior, with large clumps forming and less efficient solids packing. Powders can become more cohesive either due to increased strength of interparticle attraction or due to decreased particle weight. The ratio of the interparticle forces to weight of the particles is described by the bond number, where the more cohesive powders have bond numbers that are above unity. We can see the effect of varying bond numbers by comparing these calcium carbonate samples that were sieved into different cuts of particle sizes. Qualitatively, the powders on the right with the larger particle sizes appear smoother and more free-flowing, whereas the fine cuts on the left form more clumps. This can also be seen in the packing efficiencies by comparing each cut's bulk density, where the finest powder gives the lowest bulk density. Because these powders all come from the same fundamental material, they will have similar interparticle forces and particle densities, but they will demonstrate significantly different behavior because of changing particle sizes. Next, we can look at characterizing powder-to-air interactions for airflow through a stagnant powder bed. This is described by Darcy's law, which tells us the fluid flowing through a packed bed will exhibit a loss in pressure as it passes through the length of the bed. The amount of pressure loss that occurs will depend on how permeable the powder is, with more permeable materials exhibiting a lower pressure drop. When characterizing powder permeability, we will often measure air pressure drop for a constant gas velocity versus applied consolidation stress to quantify the powder's permeability as the bed porosity decreases. In the example data in the bottom right, the sample with the blue pressure drop curve would be considered less permeable due to its increased pressure drop. This pressure drop curve in blue also shows a greater increase in pressure drop from low to high applied normal stress, indicating that its packing was more significantly affected by the applied load. The Cozzini-Kármán equation will correlate the powder's permeability to the fundamental properties of the powder bed, showing the effect of particle morphology and bulk packing on the powder's permeability. This equation tells us that powders will be less permeable if they are finer, more tightly packed, or have less spherical particles. Permeability is a useful metric for quantifying processing behavior, as it will correlate with the amount of air entrainment a powder will experience in processing. Now we'll look at fluidization testing, where we quantify powder-to-air interactions for an unconsolidated powder as we vary the gas velocity through the powder bed. We'll find that at lower air velocities, the pressure drop will increase linearly with air velocity according to Darcy's law. The slope of the pressure drop curve while the bed remains stagnant will correspond with the permeability of the unconsolidated powder bed. As air velocity increases, so does the upwards drag force applied to the particles in the assembly. Eventually, the drag force will be significant enough to balance the weight of the particles, causing expansion of the powder bed. When this occurs, the drag force will also contribute to separation of particles in contact, which requires more force for more cohesive powders. If the interparticle forces are lower than the force of gravity, the powder bed can become completely fluidized, where the particles are completely suspended and separated from one another due to constant airflow. When the powder goes from a fluidized state back to a stagnant state by lowering the air velocity, hysteresis in the pressure drop curve will develop. This hysteresis occurs because a packing in the powder is loosened as the particles are separated during fluidization. Thus, more cohesive samples will demonstrate more significant hysteresis, as more of the drag force had contributed to separating the particles rather than suspending the particle weight. We can use the hysteresis of pressure drop curves during fluidization testing as a way to quantify the strength of cohesive interactions relative to the weight of the particles in the powder. Here we can compare fluidization behavior for two samples of calcium carbonate powders with different particle sizes. Because these are both from the same fundamental material, they will have comparable interparticle forces, but will display different levels of cohesion due to changing particle sizes. The finer material on the left can be seen lifting and collapsing due to relatively low particle weight compared to the interparticle forces. In contrast, the coarser material on the right displays more even fluidization because of the less significant interparticle forces. Thus, the particles in this sample can be easily separated once the airflow is significant enough to suspend the particle weight. Looking at the pressure drop curves as these samples are aerated, we can see clearly that the coarser powder has a lower slope in the low air velocity region. This suggests this sample is more permeable, which would be expected for coarser powders, according to the Cozzini-Kármán equation. We can also observe that the hysteresis is less significant for the coarser sample because less drag force from the airflow is needed to separate the particles in contact relative to the drag force needed to suspend the weight of the particles. The differences in hysteresis during deaeration is evidence of differing levels of cohesion due to different particle sizes between the two samples. Here is a more complete dataset quantifying cohesive interactions for different size cuts of the calcium carbonate powder we saw before. In looking at the pressure drop curves, we can see clearly that the finest cut, SL10, demonstrated the most significant hysteresis, suggesting this was the most cohesive sample. This was further evidenced by the sample's decreased loose solids fraction and increased compressibility, which suggested this sample had less efficient packing due to stronger cohesive interactions. In contrast, the coarsest sample, SL80, demonstrated less hysteresis in fluidization testing, as well as lower compressibility and increased loose solids fraction. This suggests that the increased particle weight for the sample offset the interparticle forces, so the sample displayed less cohesive behavior. The intermediate size cuts of SL45 and 15 demonstrated intermediate behavior in terms of pressure drop hysteresis, loose solids fraction, and compressibility. This is evidence that the absolute strength of the interparticle forces was comparable for each of these size cuts, but each sample demonstrated different levels of cohesion due to changing particle size. It should also be noted that these samples demonstrated comparable results in shear cell testing, suggesting that they have similar frictional interactions between each sample. This suggests that any differences in behavior of these samples is due to effects of cohesion rather than due to effects of friction. In conclusion, powder-to-air interactions are important and will contribute directly to performance in many industrial processes. Additionally, a powder's behavior and interactions with airflow will depend on the bulk packing and the relative strength of cohesive interactions between particles. Thus, understanding powder-to-air interactions is important for successful handling of powder materials in applications beyond ones that apply airflow directly through a powder bed. We also discussed how powder-to-air interactions will vary for powders of different particle sizes and how changing particle size contributes to the cohesiveness of the powder. Both permeability and fluidization testing can be used to quantify powder-to-air interactions and improve our understanding of the powder's behavior and process.